好，各位老师、各位同学，那我们现在就开始这个礼拜的量子资讯专题演讲。Okay. So today we are very happy to have Professor Lin Jun-Da from the National Taiwan University to give us a seminar today. Professor Lin got his PhD at the University of Michigan in 2010. And then he worked as a postdoc fellow at the University of Connecticut and also the Harvard University. And because of his excellent research, he was recruited by the NTU and now become a faculty member at the Department of Physics. And Professor Lin's research area is in coherent system and ion trap, and also its applications to quantum information science, and also the cooperative phenomena and superradiance. So today he is going to talk about scalable quantum computing with trapped ions and phonon laser. And that's a welcome, Professor Lin.
Okay. Thank you. Excuse me. Oh, thank you very much. Everybody hears me? Okay. Right. Good. So first of all, I'd like to thank Professor Zhou for inviting me here to share our recent work, especially on the topic of scalable quantum computing, which is kind of a hot area recently. And especially now, the ion trap system recently just got attention much from the planet. And also, so today I would like to focus on the most important part, which is called scalability, how to scale the system up. And also, if we have a large scale system, then what can we do? And I guess, of course, we can do a lot of things. Of course, for the applications on quantum computing or quantum simulation. But now I want to give you an example. Like I would like to do some kind of quantum optics simulation, which is analog to the typical problem considered in quantum optics. And now I take an example like photon laser. I will tell you what phonon laser is in a minute. Okay, so today here's my outline. So basically, I would like to give you a short introduction to what the scalability is in the quantum computing. And then, of course, now we are working on trapped ion systems. So basically, I would like to give you some idea of how this system works. And also, then I will go to the scalability challenge, the issues, and what kind of proposals now are going to be started to be used recently in many groups, and especially some commercial companies. And also, for the next part, I will talk about the phonon lasing. So, I would like to thank my students first, and of course, as well as my collaborators. So today's topic was mostly done by my PhD student, Zhenyu Li, and also some work in progress by Peng Wenhan. Okay, and actually these three guys are mostly working on the trapped ion systems, and the other three mostly worked on the dipole-dipole interaction in light ensemble interaction. Okay, and also my collaborators from Zhang Mingxian, from AstraZeneca, including Dr. Zhang Mingxian, Chen Yingchen, and Ren Xianghua. Of course, the founding agency, of course, including the Ministry of Science and Technology in Taiwan, and also the Center for Quantum Science and Engineering from NTU. Okay, so I guess I don't have to mention, to emphasize more about the quantum eras here. We can actually look at the manifesto proposed like 3 or 4 years ago by EU, and actually they map out the roadmap of the so-called quantum technology, including quantum communication, quantum simulations, and quantum sensor, and also quantum computing, of course. And of course, this is a Venn diagram I draw included in the recent proposal proposed by NTU for the National Center for Theoretical Science. And of course, I think you can look at the manifesto like 3 or 4 years ago. They actually don't explicitly include the so-called machine learning and AI. But now for the recent years, this topic has become so hot. So basically, we have to include that, of course. And now, I think the key targets will be like quantum hardware engineering, which I'm more involved in this area, and also the quantum information and communication. I think the hub is now in Cheng Kung University, and also the interdisciplinary part, like quantum computing and other applications. Okay, so I think we can just got some idea from looking at the fund invested in by many countries or organizations for the recent years. So for example, like EU, they have like 1 billion EU dollars over 10 years since 2018, and US spent like 1.2 billion in this National Quantum Initiative Act. Again, also in from 2018, and China spent like 10 times more than this amount, like 10 billion. Okay, and of course. The overall is still unknown because they are still increasing the funding amount, the funding size. And even for the India, they also they invest about 1.2 billion on this technology. And how about Taiwan? So we still have a long way to go. Of course, how I not started with to ask government to invest money. All right. So I think. For now, people working on this area are kind of pursuing the so-called quantum supremacy, and this idea was proposed by John Skill from Caltech. And I think, in simple words, the quantum supremacy just means at some stage, at some moment, then the quantum spirit machine started to be more powerful than any classical means, and one way to achieve such quantum supremacy would be run an algorithm on the quantum computer which solves a problem with super polynomial speed up relative to the classical machines. So basically now it becomes a holy grail, at least for recent years. Okay, but now I think we actually have a so-called daily life quantum supremacy. What's that? Because quantum begins to dominate everywhere. For example, like we have quantum measurement, and quantum marketing, quantum healing, and actually this is a real shop because actually I lived in this area. This was a photo I took by, taken by myself, and quantum wealth, and quantum leadership, and so on. And this are from a very famous movie, right? Endgame, Avengers. So well, basically people tend to add quantum in front of everything. And not even this, we can have more, like quantum food, and also quantum taco. All right, and this is a quantum spa, see that? And we have a sea of quantum. Okay, not a very big ship. All right, so, just kidding. So now I want to jump to the main topic, the main materials like scalability in quantum computing. So, of course, we have to examine what scalability is in this system and how to quantify it, and of course the scale of art. Okay, all right. So I can have a very brief view for this overview for this, and I think the data here, result here, is already outdated because now we have all way through this until recently. So basically now, I think these are many milestones we probably you already have read from the newspapers and also some the scientific reports. And so I want to mention that, well, I think IBM is a game changer, and also as well as Google, because they kind of announce the quantum computing cloud on Surface. So basically, you can apply an account and do some algorithm on it, and we will give gain some quantum experience from that. And of course, I think they did this from since 2018, and also up all the way to recently. And actually, the most recent machine will be here, Montreal, right? Montreal and Eagle, and also I think you may already read from the newspaper that in China they announced that they have a 9张, or they have they based on Gaussian boson sampling with 76 photons. Sorry, I did a typo here. All right, and we can actually prove in principle that if you want to overpass the quantum the classical machine by using quantum computer or quantum any machine. So basically, you only need 50 photons. So basically, they claim they have already reached the so-called quantum supremacy. And I think the most impressive part is IonQ benchmarking on 11 qubits. And actually, they proposed another measure called algorithmic qubits. And I will let you know what it is later. And then Honeywell, they also released a 32-qubit quantum computer, which realizes algorithmic qubit of 22. And actually, these already beat by huge amount those machines based on superconducting qubits. Okay, so all right. So what the scalability is? Okay, so you may ask, or you may imagine that. So we just add more ions, or more qubits, and allowing more gates. That will be the basic requirement for so-called scalability, right? But how to characterize it? Okay, and I think, of course, we pursue, in principle, so-called arbitrary scalability, right? But usually, it's very hard. It is very hard issue, a hard challenge. So basically, we have to step a little bit back to pursue so-called practical scalability. So we can have a short-term goal, intermediate goal, or long-term goal. And I think the short-term goal for us, as I said, we want to accomplish the so-called quantum supremacy. Of course, the supremacy or so-called quantum advantage. Okay, but for the intermediate stage, we have the NISQ algorithms, so-called noisy intermediate scale quantum, because now the true machine, the actual machine in nature or in labs, basically have very noisy environment around. So basically, it's very hard to get fidelity higher than some ratio which we can correct all the errors. So but now still we are thinking to get some sense or even develop some algorithms so that we still can accomplish some missions. So it's called the noise intermediate scale quantum algorithms. Okay, and again this so-called NISQ is actually invented by John Pascal, who also invented the quantum supremacy terminology. So basically, well, he get a lot of insight from just inventing these words, fancy words. Okay, so now I want to answer the first question. So basically, the very question, what is scalability is. So I think the characterization of scalability is we can just use the so-called quantum, the performance or performance to get some sense of the so-called scalability. So I think this is a concept proposed by IBM scientists. So basically, they try to think about abstract square circuits. Now it has n qubits here and also n steps here. So it's a square circuit. Okay. So basically, now we can compare this to an actual machine. If we can transfer any mission which can be done by this abstract quantum circuit to the real machine, if the real machine can accomplish this mission, basically we can claim that this machine has a quantum volume equal to defined by 2 to n here. So you can recall that IBM claimed that they now have a 128 quantum volume, which means they have this n to 7. Okay, so that means you have 7 qubits here and 7 steps here. Of course, if this is going to be covered all the possible algorithms, then you might think that, well, these qubits must be, have a full connected to each other in order to accomplish this. Okay, so basically we need more qubits of physical connectivity and of course the high coherence time over the gate time ratio and high fidelity equivalent to low error correction overhead. Okay. So as I said, well, if you just look at the number of qubits, it's not enough to give you the idea of performance or scalability. We have to also to look at the connectivity here. So this is 21 qubits fully connected to each other. And this is also the 21 qubits, but they only connect to nearest neighbor, or maybe the next nearest neighbor. Okay, but of course you can think this one can accomplish more missions than this one, of course. Okay. So I think trapped ions are the most scalable approach for short-term NISQ. Okay. I think this claim is not invented by me, because I think some of you might already attend the Young Researcher Forum last year, and this word actually I cite from I quote from Jonathan Holm last year. Okay, and now I want to persuade you that actually we can actually replace this short by intermediate. Okay, and why? What's the possible proposal for doing that? Okay. So, well, oh no. Okay. So why do we use ion trap or trapped ions? What's the advantage of that? And who are the players? Okay, and of course, what's the working principles to do this? And also, I will give you some idea of qubit and logic gates. All right. So why trapped ions? I think I listed the main advantage associated with this system. The first one is, of course, the long coherence time, T2. It can be up to hours. And of course, if you look at T1 can be even longer. It can up to months. Okay. So I think the record of like 1 hour or 1.5 hours, I forgot the real number, but it was just done by a Chinese group, Ki-Wan Kim in Tsinghua University in Beijing. Okay, and of course they have an exceptional fidelity, and of course the ions are natural natural entities, right? So basically they are all equal to each other, identical to each other. So it's perfect identical qubits. It's not like any artificial atoms which you have to do a lot of calibrations to make them indistinguishable. Okay, and of course in principle they can have all-to-all connections. And why? And I will let you know in a minute. Okay. So I make a plot like this. So basically I want to show you some idea about. So this is the gate time, and this is the decoherence time called characterized by T2. Okay. So actually we can see here we have two groups here. One is the superconducting qubits, and one is ion trap groups here. And if you, of course, typically the superconducting qubits operates faster by about 1 or 2 orders of magnitude than the trapped ions. Okay, so this is why for the gate time they are lower here. I mean the gate time is faster here, but T2 actually ion trap trapped ions can have a much longer T2. So if you compare if you compare them by their ratio, why? Because the coherence time means before the quantum information get lost, how many gate operations you can do here, right? So the ratio will tell us this. So basically now we can show, okay, this is a state of the art. I try to look up almost all the papers which show you, which give me some specs of the superconducting qubits, and I just plot according to the best T2 can get, we can get, and the best gate time we can get here from, they are not necessarily from the same paper. Okay, I just put them. That means that gives us some idea that the possibility that we can accomplish this state of the art here. But if we draw this dashed red line just indicate the same ratio here. So basically, in terms of ratio, this one will more or less comparable to this one. Okay, but for the state of art of ion trap specs, actually it lies here. So it means the ratio can be 4 orders of magnitude larger than that, which means we can actually operate, more gates than superconducting qubits. That means we can also increase the connectivity by doing this, okay, by doing the gate operations. Okay. So how about the players worldwide? For here, I show all the ion trap groups on this planet. But of course, it's already. I mean, this is not of course, it's not all. It's not the whole list, but it's actually recorded by this. You can look at this website, and this website from University of Innsbruck. Okay, they have this website and showing what's going. I mean, how many ion trappers on this planet. Okay, and we can actually see there's no Taiwan here, right? Taiwan has no any groups. So, sorry. Yeah, right here. Okinawa, Chongsheng. Yeah. Actually, you can go to this website and actually you can right-click on this small mark, and then it'll show you. Okay. All right. I want to mention that also. Now there are 5 companies. Okay, they are still to gain investment or to attract investment, and of course including the IonQ, I think, and Honeywell, and this Universal Quantum, and this Universal Quantum is from sorry, I forgot. It's also from Brighton in UK. Okay, and Oxford is from Oxford, of course. All right, and this AQT is applying quantum technology from Peter Zoller's the big team there. Okay. All right, it's not that many, but I think it's actually prospering. Okay, prospering. All right, so actually you can also find a complete list for the ion trappers. Okay, so now we have about slightly more than 100 groups. Okay, of course I say it's not complete. It's not a complete list, but now it's already summarized all the big groups already. Okay. All right, so I think it's good to look at the Honeywell. They actually claim this. They already have the 2 qubit gates up to like 99.2 for this H0 model. But recently they already announced the H1 model, which you can see the fidelity becomes improved as well. And then they have T1 is very long, and the coherence time T2 is up to 3 seconds, and they have full connectivity. That's what I said. Okay, a mid-curve circuit measurement. Okay, and high resolution rotations. And this is their architecture. So basically, they have this kind of rail structure, so they can move the ion around for different purposes. Okay, most important news is actually they claim that they already achieved quantum volume up to 512. Okay, it's equivalent to like 9 ideal perfect ions. Sorry, perfect qubits. Okay. However, let's look at ion Qs. They actually released a 32 qubit platform, and they can realize algorithmic qubits of 22. And this means, of course, they have 32 physical ions, physical ion qubits, but they can do some error correction. And they have a fault tolerance overhead. It means they can use 13 ions to correct to get the one ideal perfect qubit. And for that, they can realize. Of course, these 13 can be can be recycled. So basically, they can realize 22 ideal perfect ions qubit. So basically, we can look at. Remember on the slide I show you what the quantum volume is, right? If you have a 22 fully connected platform, basically you have quantum volume 2 to 22. So they claim they have quantum volume up to 4 million. Okay. Yes, still. Right. So actually, they basically trap the 32 ion on one-dimensional structure. But as I said, okay, I will tell you later. So basically, they share the quantum bus from the motion. So basically, every ion or every qubit share the same motion, basically, so they can have fully connectivity. Okay. Here. All right. So it's very impressive. So I think I have saved some time by skipping this slide. But basically, I want to also mention that universal quantum, they are based on, they have this kind of modularized design. So they claim they can build a scalable quantum computer. Okay. So let's briefly look at what the Paul trap is. So Wolfgang Paul, again, Nobel Prize in 1989 by proposing this trap. Basically, now we can see this is a 4-rod structure. So the diagonal wires will have the radio frequency oscillating voltages, and for the other diagonal would be the DC voltages. So basically, at some time snap, basically you can see this quadrupole like a saddle point type of potential shape, but of course, since this voltage is oscillating from this radio frequency, so basically the field direction will change with time, basically, right? So if you tune the frequency right, you will get this. So this sphere experiences a saddle point potential like this. But if this potential is rotating, so equivalently, this sphere will experience an effective potential if a confinement to this. And then now, so we can actually confine a lot of ions in the one-dimensional structure. So this is basically how the ion trap computing platform is formed here. Okay. So they have a different variations. Like this is the 6-rod scheme, and this is a 4-rod scheme used by Black's group, and this is for in Chris Barrel's group. And of course, this is all kind of outdated because now the real architecture will be like so-called planar trap or surface trap. So basically, they deform this, but the diagonal radio frequency electrode to a plane. So like they have an in-plane structure like this, and we still can find the local minima here. So basically, the ion can be trapped here. Okay. So this is from the Sandia National Lab, and this is from NEST. Okay. They designed this kind of scalable the surface trap, and because this design, so they can kind of realize their system on chip. Okay. Okay, and of course, the motional spectrum will play a role because, as I said, it plays a role as a quantum bus, which can be used to help the quantum information communication between different qubit ions. And of course, now we can gain some ideas like this one was corresponding to center of mass motion, and this will correspond to zigzag motion. And for the transverse mode, we can have a center of mass like this, which is high is the motion, high is the frequency motion here, and the zigzag becomes lowest. Okay. So because of this motion, and when we try to look at the whole Hilbert space spanned by this motion and also the internal states contained in any ion qubits, basically we can have a so-called band structure, a sideband structure like this. So basically we have a ground state, excited state, which may be treated as a 0 and 1, okay, when we try to encode the qubit information here. But again, they still can have the different, phonon modes, which is represented by this Fock quantum number, okay. And if we look at the interaction Hamiltonian, it will like this. This will be like a spin. This is a spin operator, and this will come from the phase carried by the photon, the light lasers or lasers beams. Okay, so you can actually expand this, and you get three groups of interactions. Like this one will be correspond to a so-called carrier transition here, and for this one, it will correspond to the red sideband transition here. So this one will correspond to the blue sideband transition. So in order to excite different transitions, you can actually tune your laser to have a appropriate detuning to realize or to excite the specific transitions. Okay, so that's how we control this system. Okay, and this is called the Lambda Key Parameters. Okay, and it can be understood as the ratio between the x naught. X naught is actually the wave packet, the packet width of this local motion of ions, and the ratio for this to the wavelength of the laser beams, basically. So you want this Lambda Key parameter to be as small as possible in order to have this expansion valid. Okay, so basically it just means when you shine a laser beam, of course laser beam carry a wavelength here, and you don't want the motion to move so largely, compared to the wavelength. Otherwise, you can experience different, like field gradient in space, which is unwanted. Okay. All right. So so what's the working principles? So we call now. I just give you one typical example. It's not the all. Well, there are still many other proposals, and which can be applied to different situations. So now this is a typical so-called the Momo-Sorensen-Milburn gate. The idea is like this. So basically now we actually make use of the hyperfine structure, hyperfine states associated with the ion, and now this is spin up and this is spin down, or this is a 0, this is a 1, whatever you call it. And of course we have to make use of the third excited state up here, and then of course now we can shine a laser beam, two laser beams, or like bichromatic laser beam. Basically, we have shine two laser beams with slightly different frequencies. And why this is important, I'll let you know. So basically now this laser beam only couple. These laser beams only couple this up state and the first and the excited state. So basically, any state up here will experience this transition, not this state, right? So if your qubit is somehow in a superposition of 0 and 1, or up and down, then only the up part will get this field or force, and the other part will lift nothing. Okay, so it's called spin-dependent force, and which is very important. Why? Because so now, in order to get the integrity gate, now we are demonstrating the so-called control phase flip. So basically now we have the truth table like this. So if we have a down, then it still remain the same, and up it remain the same. And if you have a down up, then you will gain a phase like this. And phase is from what? From where? From this the area enclosed by these phase trajectories. So in order to get this circle of phase trajectory, you have to push the ion. Okay? So of course the ion is already in some motion, but without any force, it will do just as simple harmonic motion, right? As we learned from the textbook. But if we go to the rotating frame, then this motion will just stick to the same point. If you move at the same frequency frame, along it, as it, there's no any additional phase here. So in order to get this shape, this additional loop, you have to kick the ion. Okay, basically that's the idea. So now we want to what? We want to do what? We want to do if this gate, this ion is partially in the up state. Only the part state will get kicked, and will give you this additional phase. But the down part will get nothing, right? So that's how we can get this. So if we have a down up, we have additional phase here, and if we have up down, we also get this phase here. And if you look at this truth table, and you already can get the so-called control phase flip. Okay. And of course, the direction of these two laser beams also give us to control the direction of kicks. If you shine a laser beam like this, then that because they differ by a the small frequency here, and this frequency is called bit node frequency, right? As we learned from the university physics, we already know if the two frequencies differ by a slightly amount, then the difference will become the bit node, right? So basically now, it's the bit node frequency which can be made comparable to the motion frequency of the ion. Otherwise, this transition is typically like up to hundreds of terahertz. So it's no way to use this only single transition to drive the motion, right? So in order to drive the motion specifically for for some motion modes, basically we have to tune this detuning right in order to excite some modes you want. Okay, so this is a bit node frequency. Basically, we can write down the Hamiltonian, the interaction Hamiltonian. So it looks messy, but actually it's very simple. It can be simply answered like this, because now it becomes a force term, right? Because now force is a periodic force given by this bit node frequency, basically, right? So you have a force term like this, with the frequency mu here, and this one is just the different representation of x. So this is F times x means work, right? And now because now it's a spin-dependent force, basically we multiply it by a spin operator here. So that's a single ion qubit experience the spin-dependent force, the interaction Hamiltonian just look like this. And what if you have multiple qubits? Then it becomes a bit more complicated, but still understandable, because now you have to diagonalize your motion to form normal modes. So you have to sum over all the normal modes. The k means the mode index here, and ak just means the phonon operator of the mode k. Okay, so pretty much the same. Just you have a summation here. Okay. So again, this is called Lambda Key Parameter, and of course you can write down the evolution operator from this Hamiltonian. Basically, you have the first order part and the second order part, and this will give us the desired force, because now the sigma z means the spin interaction with the coupling here, and this coupling will give you the phase. Okay, but we also have the first part. First part will contain the unwanted phonon, i.e. motion, to the internal state entanglement. We don't want this. We have to get rid of this. then so this part need to be engineered to be got rid of. So that's why we need some sort of pole shaping to do that. So I give you an example like this. So now I do this on a 2,000 ion array. I mean, as a one-dimensional array containing 2,000 ions. Okay, but now I want to do something to entangle two adjacent ions. Okay, so this is the pole shape I found. After doing this pole shape, then this is a trajectory in the phase space. And after doing that, I can get the entangling gate between these two ions with the with the error only like 10 to minus 4 or 10 to minus 5. Okay, and I also demonstrate remotely entangling two ions. Sorry, this adjacent here is not. This adjacent should not be here. Okay, so I want to entangle two ions separated by 9 other ions. So we can basically do, the remote entangling gate. Okay, so of course the pole shape becomes a bit more complicated, but still it's doable. And of course the error is also proven to be like suppressed like this. Okay, so that's the idea. Oh, that's what I mean by fully connected, because in principle, any two ions on the same string can be entangled. Okay, the only question is how much price we need to pay. Okay, all right. So what's the challenge in scalability? And any proposals? So of course, to scale it up, the first thought is to add more ions into it, right? So that means we have to build a larger trap, of course, in order to get the so-called single ion or single qubit addressability. When you shine a laser beam here, you only want to shine one ion on one qubit without causing any crosstalk between different adjacent ions. So basically, you have to keep the spacing between adjacent ions to be up to some size. Like for example, typically it's like 10 micron, a few micron basically. So now we have the current technology of the focus beam can be down to like a few micron as well. So 10 micron should be safe. Okay, but if you want to add more ions into it, and then you have to think about what's the possible architecture to hold all the ions. Okay, so of course this is a one-dimensional structure. So if you have a harmonic trap like this, then without considering the uniformity of this system, then of course if you have this kind of shape, it will cause so-called zigzag transition, because this part will become very the spacing will become very narrow. Okay, so it causes so-called a structural instability called zigzag transition. However, if you want to avoid this, you have to make the trap shallower as well in the same time. So that means, well, if you want to, the transverse potential frequency is less than, in this example, is less than the 0.3, then it will cause we will have a zigzag transition here, and of course we have to think about the homogeneity and also structurability. Okay, so in order to avoid this, we have to kind of make the spacing as equal as possible and make them always comparable to like 10 microns. So in order to do that, we have to think about how to design the architecture, how to design the trap. Okay. So I think there are many strategies. The first one is like we can break the array into small pieces. So the first one is called ion shuffling. So basically, we have this kind of segmental structure, each one corresponding to a voltage. Electrode can have a separate voltage. So you can actually change the voltage and make the ion move along these rails. Okay, we can move around. Okay, and for different regions, they have different purpose. For example, this region is for storage, and this region is for interaction. So we can move the ion to there to interact with others, and then move it back. Okay. Another one is called the quantum network. It's actually use the optical links, for example, like fibers or waveguides, to communicate, to help communication between different small traps. Okay, it's called quantum network. All right, and let's look closer to the ion shuttling. Of course, you can imagine if you want to use this architecture, then you have a lot of issues associated with the motion control, right? Movement control. So, well, actually, you can also look this up at YouTube, because the Universal Quantum, the company, announced the so-called their blueprint for microwave trapped ion quantum computer. Actually, you can see how the ions move around along this module and modularize the rails, and then they can do that. But to save time, I don't want to show this video here. But well, please do this because it looks very interesting. Okay. But point is, okay. So basically, people already took a lot of efforts to look at this possibility. So, for example, like in Hansinger, in 2006, they kind of look at the so-called T-junction here. So they try to look at how the ions move around this corner and still get very high fidelity. And this is X-junction proposed by NIST in 2009. And this also from Holmes group, X-junction. And this one is X-junction, but it's realized in a so-called surface trap. Okay. And of course, this Honeywell architecture, they also use this. Okay, sorry, I forgot to mention. This architecture is called quantum CCD. It's like you know, CCD we use in camera, right? But it's called quantum CCD. Okay, so basically Honeywell actually make use of this QCCD architecture. Okay. So this is the roadmap of scalability proposed by Honeywell. So basically now they have H1 here. Okay. And in H2, which they are designing now, they will form like a closed loop, like a field track shape here. And for H3 or H4, even H5, they start to think about how to realize this in a grid, and structure. Okay. All right. So let's also look at the possibility of the strategy of a quantum network. So basically, one example is to realize the ion and optical, for example, like photons, through some sort of quantum interface is used at the DLCC protocol. Okay, and the big issue associated with that is will be discussed in the next slide. So of course, in the long run, pretty much we okay. So maybe at some day we need to combine all different advantages from different physical systems. Then we have still need to look at or need to investigate the so-called quantum network, because it's kind of, you know, future is a goal in the long run. But for now, if we want to do something which can be done in the NISQ stage, like noisy intermediate scale quantum, then actually this one will cause other issues, which is really important. Is very crucial in this area, in this strategy. We can make a short comparison here. So because we are comparing the ion shuttling network and also the typical stationary array. So of course now we can think, we can imagine that the architecture and application is very complicated in this ion shuttling, because you have to design the QCCD, right? And of course this one is relatively easier because it's just, you know, one-dimensional RF trap, okay? And this one needs movement control. And entangling, but the big issue associated with the quantum network is the entangling needs to be probabilistic here. Okay, because, you know, ion has some, finite absorption cross-section toward the photons. So basically, so the entangling cannot be done deterministically. Okay, and of course, this one needs faithful interfacing because they have to negotiate different, communicate with different physical systems with different physical, for example, limit like frequencies, frequency range, and so on. So, and of course, cooling was needed for every realizations, but now this one is highly required. And of course, if we have a very large array, then it also requires very serious cooling technology. Okay. So other strategy is called 2D arrays. So there are other possibilities like it's planning trap. It's called planar panning traps. So there are different ion traps using magnetic field. Okay, and this one is still still using the radio frequency trap, but now they intentionally to use the the zigzag transition, and even more they can squeeze. If they squeeze the trap more, they can form multiple zigzag or even helix structure, and they want to use this as a platform to do as a 2D array platform to do quantum computing. But of course, this also this idea was proposed, but it's still under investigation. Okay. So there are other possibilities like micro traps, and I think I just give you some idea like this, and we'll skip this slide. And other strategies, well, I think it's also very important to look at what's the fundamental limit of the 1D structure. Because once you know the fundamental limit, which can be also very important in different realizations. Okay, for now, well, as I said, the uniformity becomes very, very important in large-scale quantum computing. So how about we design a trap like this? It's called the bookend-like confinement. And if you want more ions, you just separate these two ends more, bookend more, so to hold more ions, right? And if this is a box-like potential, then the middle part of the array can be made extremely uniform. So that means if you do a quantum gate here and quantum gate here or quantum gate here at different positions, you always require only the very similar controlling parameters like a laser power or the choices of laser frequency and so on. Okay, so that's very important. Okay, so that's the architecture we propose. So basically now we have this kind of surface trap. With this extension of linear architecture. And the second issue is, well, you may imagine this array is very hard to be cooled. Why? Because now the whole array will experience a very shallow potential, right? So I always give an example like海盗船 in play, 游乐园. So basically you have a very heavy, massive object, then they will swing very slow, right? So basically the frequency of this motion is extremely low. And if the frequency is low, then any given finite temperature will heat it up. Basically, it will cause a very serious issue. And also, this ion will move off the sides. Then when you shine laser beam, the laser beam will cut nothing, right? So basically, that's very terrible. So how to overcome this difficulty? So we propose to use optical tweezers here. Okay. So we showed that if we tune the optical tweezer frequency, the tweezer strength, and this is lowest frequency, and this ion numbers up to like thousands. So basically, we show that if the tweezer frequency is up to megahertz, then these ions will be effectively pinged in space. Okay, so the laser frequency will pretty much determined by the local motion of this separated, isolated region, isolated sub-arrays. So that means we can actually raise up the laser frequency, and we can show if this array is cooled by the so-called Doppler cooling technology, then it already can give us a very high fidelity without concerning, you know, the divergence of the motional state. Okay. So I think this is a very quick conclusion for this part. So basically, we want to emphasize that we use optical tweezer to assist the to help stabilize the 1D machine, the 1D array. So typically, Coulomb force is much stronger than dipole force than optical tweezers. But if for uniform array, most ions see extremely fast potential, and the next order, the Coulomb interaction will be cancelled out when they sit around the equilibrium. So the next order we have to worry about is the next order residual Coulomb interaction, which will typically comparable to the frequency strength of the optical tweezer. So that's why optical tweezer can play a role here. Okay, so it tweezers of like 10 times of omega naught. Omega naught means the characteristic frequency for the phonon exchange between adjacent ions. So you're 10 times that. So you're about the megahertz. So you'll effectively ping the ions. Okay. So the beauty of it is the optical tweezers can be tuned on and off freely. So it's on demand, right? So basically, it's very flexible. Okay. So it can help stabilizing and cooling the structure. And we also have some results of doing the so-called local sideband and Yeti cooling, which is still in preparation. Okay. So another strategy is just to speed up the gate. Okay. And it's actually a different thinking. Why? Because the gate time associated with ion trap is about like a microsecond, okay, or tens or hundreds of microseconds, because it needs to be comparable to the motion, the time scale defined by the local motion in the harmonic trap. So what can we do if we want to get the gate faster? So there's a proposal to use the so-called fast gate. It's going to use the pulse force laser. Okay, so basically we can actually see when the ions are doing harmonic oscillation. So basically, when we shine a very strong or powerful laser in a very short time, it can suddenly kick the ion off and suddenly kick it back. Okay, so by doing so, we still can have a very large area enclosed by the trajectory. So that's how we can speed up the gate, still get the pivot force phase here, and this is a different proposal, and use a continuous laser, but still can do very fast gates. Okay, and so actually we can already prove that papers can be found for theory, like the gate time can be like smaller than 1 microsecond. And this one is also have the is comparable to 1 microsecond. Is already demonstrated in experiments. Okay, so you can see very impressive. Like the gate time can be like 0.48 microsecond. It's very fast. It's already like 1 order of magnitude slower than a superconducting qubit. The superconducting qubit can be up to like 10 nanoseconds, which is very fast. But the decoherence time is horrible, right? But now the gate time is gradually catching up with the superconducting qubit. All right, so I think I should skip this part. But the idea is there is other approach, like we shine laser beam here and make the ion move through it, and in order instead of shine the laser beam on stationary ion, it's called transport gate. And actually, these laser beams can be reused simultaneously by many ions. So it's called transport gate, and it's interesting. I just show you here. Okay, so how many? It's already. I used up the time basically. Oh, sorry. I just give you a very short idea of brief idea of how the phonon laser is. So basically, I skipped this part, and there are some applications of using phonon degrees. Okay, so why is the phonon laser interesting? Because what is phonon laser? Phonon laser is an optical mechanical system in which optically furnished GaN enables self-sustained mechanical oscillator, are probably called a phonon laser. Okay. So of course, it's a fundamental similarity between optical and acoustic laser, acoustic excitation, and slow wave packet is good for phase control, right? It's not like the optical laser. A motion-induced coupling between ions and atoms can be deterministic, which is very important, because as I said, when we look at the cross section of the light and an atom interaction, the cross section is finite. That means the process is probabilistic. Okay. So the idea is like this. It's very simple. As long as we now can construct a very long array here, so we basically shine laser optical tweezer here, and as I said, if the tweezer frequency is as strong as megahertz, so basically it can form a partial mirror for the motions confined in this area. So it's like optical resonator, but now it's a phonon kind. It's a phonon resonator here. So now we can also pump the motion for this sub array. Basically, we give it energies and make the energy, make the excitation, move back and forth here, and do like some sort of lacing. Okay. So it's like a guitar string, right? So we just clamp here and make this part move. Make this part move, right? So we write down the Hamiltonian, and basically we take this part as bath and only this part for system, and we trace out the bath part. So we can end up with the effective cavity loss like here. It can be done here. So we can now, so I can show you this is cavity loss basically, okay? And there's a number of tweezers. So the 1 plus 1 means 1 on the right and 1 on the left, okay? And this number can be tuned as well. And now, because now we are looking at this 5-ion subarray. So there are 5 ions sandwiches by these tweezers. So basically, so now we can have 5 normal modes here. So when we okay, so we can actually check if this bath is Markovian or not by looking at the evolution trajectory of this. Okay, so we can see if we use a very strong tweezer, and actually the system goes like Markovian, goes a Markovian process. Okay, so this is our starting point to make this phonon to lace. Okay, so again, this is how we pump the cavity. So we use the blue sideband the Raman or sideband transition to do that in order to get the sufficient resolution, and that's the result. So basically, we can look. We can get the gain and a threshold behavior by looking at this equation motion, and I just show you the figures. So, okay, so this only for a single ion or situation. So means because due to some calculation load, we can only accomplish the calculation for n equal to 1, n equal to 2. But now this is for a single ion case. So we can basically get gain as a function of this eta omega is the pumping strength. So as the strength increases, we can get the gain up to we can gain approaching to infinity at some point, and this is exactly the threshold behavior. Okay, and we can also look at G2. G2 means the second order coherence measure. So basically, we can initially we have a 2 here, but when this system get to lace, we can get unity coherence here, suggesting the lacing, right? Emergence of lacing. And we also look at the phonon number, the mean phonon number within this, this resonator. So basically, we can get the population microscopically. Okay. And we also look at the phonon number distribution. And although depending on different noise level, we cannot get as perfect as this Gaussian, this Poisson distribution. But I think this is typical also in the optical cases. Okay, so we get broadening here due to the noise level. But if there's no noise level, actually this system can present the Poisson distribution. So basically, it's a laser. Okay, and we also get line narrowing here. Okay. All right. So the the beauty of this scheme is actually it's tunable, right? It's flexible. So we can actually turn this this tweezer off, or turn the tweezer like a smaller in strength, right? So we can basically study. This allows us to study propagation. Okay. So I just show you this. It means we have this controllability. Yeah, but we don't want to draw any conclusion about this. I just tell you we have this flexibility to do that. Okay. So this is interesting. Like if we look at the two ion case, okay. So basically we can have 2 modes. One is breadth mode and one is center of mass mode. And actually we can get some sort of mode competition because when we okay. So to characterize this phonon laser, we use a classical energy to characterize it. So this is a plot for this is center of mass. This is center of mass energy, and this is a breadth mode energy. And this arrow, this curve shows the time evolution directions. So basically, initially we start with this point, and as time goes by, this system will evolve into this point. And this point is actually corresponding to a microscopic occupation of the breadth mode without any occupation in the center mode. But when you look at different strength, pumping strength, then basically we can get this contribution, this kind of behavior, depending on the initial choice of your initial conditions. Okay, so when you start with this point, they will end up with a microscopic occupation of the breadth mode. But when you choose a different point, it will end up with a microscopic occupation of the center of mass mode. So it's kind of corresponding to some sort of bistability of the system. Okay, so this is a phase diagram for this, and this shows the number of the center of mass and this number of breadth mode. And this boundary, we suspect that is a first order phase transition. But of course, this work is still needs more investigation in the future. Okay, so I think I already ran out of time, and this is my short conclusion. Basically, I want to tell you that ion trap system remains the most competitive group in the quantum computing platform. And of course, the important issue is scalability. And actually, people are thinking about the solution or the resolution to this scalability issue. And also, we propose optical tweezer scheme, which can be used to help stabilize the 1D array. And oh, sorry, I forgot to scroll this out, because actually we are also working on some variation of transport gate. We should call it drive-through gate. Hope next time I will have a chance to explain that to you next time. Okay. So optical tweezer can be used to create a phonon resonator, which can lead to phonon lasing. Okay, so as I showed you before, as a future work, fast gate scheme is limit a quantum small network in NISQ regime, and cooling phonon squeezing a phonon cavity QED are all the possible directions our group is going to look at. So, thank you very much. That's all my talk. Okay. Well, I think no, right? Because it's just an analog to, I think it's the most like a weak coupling regime of the optical, right? Because actually the coupling strength pretty much given by the Lambda Key parameter times the laser pumping, and laser pumping and also the Lambda Key parameter are all small quantities. So basically, it's very hard to get that. But yes. Well, we actually didn't look into how strong we can get, but now I think the first example to demonstrate is like we want to do some cavity usually expected to do. So the laser is a typical example, right? And of course, that's the possible direction we want to invest in the future, because it actually can help, give us any any other possibilities, like we can do a quantum simulation or quantum optics simulation using this system. And because the phonon degree of freedom is actually a very different one. For example, the polarization direction is different, right? For the light, there are only two polarization directions, two transverse directions. But the phonon laser, in this case, actually we showed the longitudinal motion laser. So it's a different laser, right? It's a laser which the polarization direction is longitudinal. That's very unusual, right? But also we can also do transverse mode. But well, it's a different story. Yeah. Okay. We hope we can invest more in the future, but not now. Yeah. Mm-hmm. Yes. Okay. Exactly. Right. That's a very good question, and actually very important question. Yeah. So actually, if you remember, I actually put a question mark there. See, so-called optical connection is in principle, because well, I usually use an illustration like so. Ion trap. Ion talk to each. How ions talk to each other is like we make a phone call to, like I make a phone call to you. So basically, we pick up the phone and we actually encode our information to the phonon, right? To the vibration, and we actually the vibration here actually can be shared by all the ions. So when the gate is done, that means we have to return. By return to original state, which by that we mean actually the phonon, the motion, and then the information should be disentangled, right? So basically we hang up the phone, right? So basically we kind of decouple the motion to our speech, right? Basically, so because the motion now is collective motion shared by all the ions, so all the ions once they want to couple to this motion, we just shine laser beam to it, right? Because laser beam will help the ion to be kicked, right? And which means that's how we couple the motion and their internal state. So if, well, in principle, it can be done for any two pairs on the long string, even they are very, very long. But you can imagine that, well, when the array is very long, then there are many modes, and the modes will form this. Will give you some kind of locality, because the many modes are in principle. But when we are looking at the real response to the motion, because the motion is still kind of localized. Okay, of course, any kind of local motion can be decomposed into the superposition of all the collective modes. But of course, the real important thing is actually is still the local motion. Okay, so if you want to realize a very long long distance entangling, then the price to pay is the laser power, and also the gate time. You have to wait. Okay, so I think nowadays, if we still consider only like less than like 50 ions, or maybe 100 ions, less than that, it still can be done fully. I mean, for any 2 ions here, it can be done. And if you the gate time, if you are okay with the gate time, slow gate time, like millisecond, it can be done. But the point is, if you want it to be fast, you have to shine very powerful lasers. Okay, so that's why people are thinking to save some energy by using, instead of using off-resonant lasers, they are trying to use the pulse-forced, because the pulse-forced are actually resonant lasers. Okay, so that's one way we can save some energy. And of course, in that fast gate limit, the real reason for ions can talk to each other is actually the so-called dipole-dipole interaction. Okay, so again, if you are looking at the very slow dynamics, it's called a diabatic regime. Then of course you have to make a considerably analysis around all the possible motions. But if you go to the very fast limit, then the gate operation is much faster than other possible motion involved here. So that motion becomes, the gate, it becomes possible because of the dipole-dipole interaction. Because every qubit, every ion has a charge. So that when the charge moves like this, you form a dipole, right? And for the other immediate phonons don't have time to participate in this crosstalk, to this communication, then of course the gate can be done only due to their dipole-dipole interaction. So that's the fast limit. Okay, so the dipole-dipole interaction goes like 1 over r cube, right? So you can try to imagine what's the price paid here. Okay, so if you expect very long distance, then the coupling goes like 1 over r cube. So that you have to kick the ion even more to get enough dipole-dipole interaction. Right. So that's the reason. Yeah. Okay. Thank you.